We're going to be discussing several different convergence tests. These are going to be ways that we can tell if an infinite list of numbers that we're adding together will sum up to be something that is a finite number or if it's just going to tend towards infinity or really be hard to nail down exactly what it is. So the first one is going to be one that we use all the time. So the answer to the first question, when do I use it? I can use it on all series. On all series. And it's worth saying, and I'll write it too, that it's a really good first test to do, and often it happens in your head. It's a good first test, and it is actually not so much a convergence test as it is a divergence test, but we'll talk about it. So what does it tell me? It tells me that if the limit as n approaches infinity of the nth term does not equal 0, then the series diverges. So if I want to know if something converges or not, this is a really good way to tell if I'm wasting my time from the very beginning, just to see if it diverges. So let me give you a couple examples very quickly. And the first one is this right here. I'm going to number it number 1. If I wanted to go from 1 to infinity of 3n over 4n plus 7, and I want to see if this converges or diverges, then what I can do is find out what happens as I approach infinity. So using the nth term test, and this can happen in your head, you would say, well, the limit as n approaches infinity of 3n over 4n plus 7 equals, okay, well, we use a little bit of our algebra skills here to realize what's happening. As we get larger and larger in the numerator, we have 3 times big divided by 4 times big plus 7. The 7 becomes irrelevant, and we have 3/4. Because 3/4 is not equal to 0, then this series diverges. So this series diverges. Okay, let's do another example. Number 2. N equals 1 to infinity. We'll have n factorial in the denominator, and in the numerator we'll have e to the n. Okay, well, let's do the nth term test, just to kind of see if we're wasting our time with a convergence test. And again, often this happens in your head. The limit as n approaches infinity of the nth term, and this is the nth term, that is the explicit formula for it, e to the n over n factorial equals, okay, well, for very large values of n, we need to see what's going on here. Now, e to the n is pretty powerful. It gets really big really fast. N factorial gets bigger faster. So in terms of which one overpowers the other one, the denominator overpowers the numerator. So in this particular case, the denominator gets really, really big, much faster than the numerator does. So this approaches 0. So what can I say? Can I say it converges? No, I can't. I can't say that at all, but I do know that it's worth my time to do another convergence test on this, and we probably will later. But for now, I know that this one diverges because it doesn't equal 0. This one does equal 0, so the nth term test was inconclusive. But if I had to figure out if this one converges or diverges, then that one, this test right here, would have saved me a lot of trouble. This one is a good way of looking at it and saying, well, you know what, I don't know yet, but I'm glad I went ahead and figured that out. Let's talk about geometric series. And when do I use a geometric series? Well, if my series is geometric, well, what does that look like? So here's the indicator. It's going to be structured like this. It might go from 1 to infinity or something like that. And it's going to be a r to the n, or possibly it would go from 1 to infinity, and it would be a r to the n minus 1. And those are not the only 2 types of variations that you could have, but those are the 2 main ones. And so basically we have some starting number and then we're multiplying by the same thing every time. What does it tell me? Well, a couple things here. It can tell me if it converges or diverges. So if my common ratio r, and that's the common ratio, that's what I'm multiplying by every time. So if I give you a list of numbers, you can say, oh, how am I going from one to the next? And if I'm multiplying by the same thing every time, you found your r. So if r is greater than or equal to 1, or r is less than or equal to -1, the series diverges. But the opposite of that is true. If r is between -1 and 1, I'm going to write it like absolute value. If r is between but not including -1 and 1, then you know what's about to happen. The series, I made it all one word, the series converges. Meaning if I add all those terms together, I get an actual solid answer that's not infinity, right? Well, actually in this case, I can tell you what it converges to. It converges to this number right here. We'll call it S for sum. And that would be the first term divided by 1 minus R. There we go. So let's do a couple examples. I'm going to switch colors here. And example number 3 is this right here. We're going to go from 1 to infinity of 5 and then 3 halves to the n. Okay, and I want to know what happens here. Well, let's figure out what R is. First of all, it does fit in the structure of these. We have a number and then another number raised to some power, so I'm multiplying by the same thing every time, so it's geometric. And in this particular case, my ratio is, well, it's 3 halves. So since R, almost look like an n, R is greater than 1, and now I'm going to clarify that. You can leave it the way it was, but I'm going to clarify it a little bit. Since R is 3 halves, which is greater than 1, the series diverges. So you list these numbers and they keep getting bigger, so clearly, there you go. You could have done the nth term test on this one, by the way, and you would have been able to tell immediately, oh, as I get larger and larger n values, this is getting bigger and bigger, so it diverges. So nth term test, great first test. All right, number 4, let's start putting it like this, 1/8 the n minus 1. And for what it matters, if I was to plug in a 1 right here, then I would have, well, 0. 1/8 of 0 is 1, so 1 times 1, 1. And so I'm going to start with 1, and then I'd multiply by an 1/8, and then multiply by an 1/8, and then multiply by an 1/8. And so it is getting smaller every time. Just because a series is getting smaller doesn't mean it converges, but in this case it does because it is geometric. So R equals 1/8, and I'm going to write it all mathematical. 1/8 is between -1 and 1. So this series converges. Okay, they didn't ask this, but what does it converge to? Well, this is going to be a really easy one to figure out. So I'm going to use that formula right there in that little space that I have. And when I do that, I'm going to just find out what the first term is. And the first term will be what happens when I plug in, well, a 1. So plug in a 1. Again, we go through this and we have 1/8 to the 0. That's 1. So the sum is 1 over, I'm running out of space, 1 minus 1/8. And now we just do a little bit of math in our head. We have 1 divided by 7/8. That reciprocates it. And so we have 8 over 7. There we go. We have found the sum. We know it converges, so we're able to find the sum. There's a very obscure type of series that is not even mentioned in many calculus textbooks, but I think it's worth a mention. So it's called the telescoping series, and I will use it when the series has terms or parts of terms that consistently cancel. So let me write that down for you. When do I use it? When the series has terms or often parts of terms that consistently cancel. Okay, and you'll see what I mean by that in just a second. And then, well, what does it tell me? You'll see. It tells me lots of things. Well, let me kind of answer that by writing down what we do. So we're going to write the first several terms to determine the pattern. But before we ever do that, and I probably should have put this at the beginning of the sentence, use the nth term test first. It's always a good first test. So when I do the nth term test, if the terms aren't getting smaller and they're getting actually bigger or even just approaching 1, then I know when I add them together, then I'm going to get something that diverges, right? So I need to do the nth term test first. But then once I've done that, I can see the first several terms and then just kind of see what the pattern is. let me go back up to when I use it and write down just kind of a rough overview of what it looks like. It would be something like this, and this is a very vague interpretation of it, but it would be something like b sub n minus b sub n plus 1. This is something similar to that, like we're going to have two terms and there's going to be one that's positive and one's negative, and then we go to the next term. So let me show you exactly what I mean. Switch colors here. This is example number 5, and we are going to use just one example on this one. We're going to go from 1 to infinity of 1 over n plus 1 minus 1 over n plus 3. Okay, and let's see what happens here. So if we were to take this all the way to infinity, then we would basically be approaching 0. So sure enough, the nth term test works. Let's find what the first several terms are, and I actually could put equals here. So let's plug in a 1 here and here, write it out. Plug in a 2 here and here, write it out. Plug in a 3 here and here, write it out. Plug in a 4 here and here. And at some point, very soon, we're going to notice a pattern and say, well, I know enough, and let's just stop. So we plug in a 1 here and here, so I have 1 over 2 minus, plug in a 1 here, 1 over 4. Okay, fine. First term. Here's the second term. Second term is when I plug in a 2. So 2 goes here, 2 goes here. So 1/3 minus, plug in a 2 here, 1/5. Okay, anything cancel? Not yet. Sometimes things start canceling pretty quickly in these. All right, third term. This was term number 1. This is term number 2. I'm going to underline it. This is number 1. This is number 2. We're about to do number 3. We'll go to number 4 at least. So when I plug in 3 here, I have 1/4 plus 1/4 minus, I'm going to plug in a 3 here, 1 over 6. Automatically I'm seeing some things that are going to cancel. Let's go at least one more term. Let's plug in a 4 here, so plus 1/5. And then we plug in a 4 here, and we have negative 1/7. And so now I'm starting to see some things that'll cancel, and I'm going to go one more term just for fun. I'm just having so much fun I can't stop. And so I'm going to plug in the fifth term, so 1 over 6, 1 over 6, and then 1 over, what was the fifth term? Yeah, 8, 1 over 8. Okay, so I automatically see some things that are canceling. So 1/2 does not cancel, 1/3 does not, but 1/4 does. 1/5 does, 1/6 does, and if the pattern continued, this one would and this one would, and I'm going to continue by saying plus ... because if I'm going to have an infinite sum, then it doesn't just stop there, right? Mathematically, in my notation, I need to say it keeps on going. But what I really have is confusion, because I can't figure out which end of the marker I was writing with. What I really have is basically 1/2 plus 1/3, and that is equal to 5 over 6, and we found what it converges to. We found that it converges to 5 over 6, and so sure enough it did converge, and writing those things out led us to that conclusion, because those were the only two terms that did not cancel. And I say terms meaning terms within what I had, but this was the first term, second term. Okay? Well, here is everybody's favorite type of series. And the reason it's their favorite type of series is because it's so easy to identify and so easy to tell if it converges or diverges. So here goes. When do I use it? Well, I will use it when it is structured, when my series is structured like this. 1 over n to the p, where p is just some power. So we're basically raising something to a power, but that's in the denominator. So what does it tell me? If p is greater than 1, the series converges. Period. That's it. It's that easy. If p is between 0 and 1, including 1, then the series diverges. These are the easy ones. You just have to identify it as such. Often when we get into other tests, like comparison tests, we will compare it to something using one of these more simple ones. So let me throw one more thing in there, because there's a special name for one type of series here, and it does diverge. If p is actually equal to 1, if p was equal to 1, then that is the harmonic series. I'll just put is the harmonic. So when you hear someone say, oh, it's the harmonic series, that means that they have this series where, I'm going to erase this in a second, otherwise I'll run out of room, where they'll plug a 1 in for p, so it'd be 1 over 1 to the 1, and then 1 over, plus 1 over 2 to the 1, plus 1 over 3 to the 1, plus 1 over 4 to the 1, plus 1 over 5 to the 1. And that's the harmonic, and it just keeps on going from there. Okay, let's do a couple examples of those. And we'll switch to red. So here is example 6, and it is this. Now, I didn't write it in the most obvious form, but it's very easily manipulatable. If that's a word, I think it is. Manipulatable. So there we go. That does not look like that, but it actually could be. So let's just take a little bit of extra time and figure it out. So this is really the sum from 1 to infinity. N to the 1/4 in the numerator, n to the 1 in the denominator. And so we'll subtract our exponents. That gives me 3/4 in the denominator. So what I really have is this, and a lot of this can happen in your head, just be careful. 1 over n to the 1 minus 1/4, so 3/4. And now I just look at it and say, well, that sure enough is structured like this. And so now I have to determine if it converges or diverges. Well, 3/4 is between 0 and 1, so the series diverges. So series diverges. You can just write diverge if you want to. I like complete sentences. Okay, let's do number 7. We did one that diverged. Now let's find one that converges. So obviously you already know the answer. But the trick with these is not much, but just manipulating the algebra just a little bit to make it actually look like the structure that it is. So we'll have 1 over n times the square root of n. We'll just do that. So if I looked at that and say, well, that doesn't look like that. Well, it almost does. So that's n to the 1, and that's n to the 1/2. So what I really have is, my sigmas are getting sloppier and sloppier. 1 plus 1/2 is, well, 1 1/2. I'll call it 3/2. 3 over 2, of course, is greater than 1. So if p is greater than 1, the series converges. So this series right here, the series converges. Handwriting is getting worse too. And I made the board a little crooked. There we go. The integral test is a little bit more cumbersome than a lot of the other ones, but it is incredibly practical. So when do I use it? I will use it when a function, okay, let's stop right there, hold up. When I'm talking about convergence or divergence of series, then why would I be talking about a function? So here's what we're going to do on this one. We're going to take a series and we're going to define it as a function. So when a function defined by a series is, okay, 3 conditions that I have to meet. What are they? It has to be continuous. All right, let's pause right there. Continuous, but this goes from 1 to infinity generally, so it has to be continuous for that domain. Maybe it was discontinuous on the negative side, but that doesn't necessarily matter. It's continuous, positive, again, for the positive x values, and decreasing, again, for the appropriate domain. Okay, so what does it tell me? Well, before I tell you what it tells you, let me tell you how to tell it what it tells you, or something like that. So first, what we need to do is rewrite the series as a function. So what we're really going to do there is say, well, I have some series and it's defined recursively as a sub n, and that's going to be called, well, f of n. So basically we're just going to say, I have a function now. And evaluate from 1 to infinity f of x dx. Okay, well, when I do that, then what does it tell me? If this improper integral converges, if I can get an answer, like a numerical answer, then the series will converge as well. If I get something crazy like infinity, then the series will also diverge. So here goes. The integral and the series either both converge, put an extra letter in there, or they both diverge. So whatever one of them does, the other one does. So I'll evaluate that one using my calculus skills and then determine what happens with the other one. So let's do an example, and I'm running a little short on space, so let me grab my marker that happens to be laying around here. I'm going to write this one up here. This will be number 8, I do believe. Number 8, we're going to go from 1 to infinity. That's kind of how these things work. And it's going to be n over n squared plus 4, and we're going to raise it to the 3rd power. Okay, well, when I look at this, I think, well, maybe it would be a function. And if it was a function, then do I meet these 3 conditions? So is this thing for positive, for 1 and forward, for 1, 2, 3, 4, 5, 6, all the way to infinity, is this thing continuous? Yes. Is it positive? Yes. Is it decreasing? Yes. That one may not be as obvious, but you can test it on the calculator. But your denominator is getting bigger faster than your numerator is, so it is going to be decreasing. So because that is the case, then we will be able to define this as a function and evaluate it. So here goes. We're going to figure out what happens as we go from 1 to infinity of this, but let's call it x instead. So x over, get this thing to hold still, x squared plus 4 cubed dx. Okay, well, that's kind of illegal just to leave it like that. We need to find out what happens as we approach infinity because we can't plug in infinity. So it is the limit as b approaches infinity. I use b because I like a here and b here. Use whatever letter you like. So I'm going to go from 1 to b of x over x squared plus 4 cubed dx, and we'll continue to go from there. And as we do, this would involve u substitution. I'm not going to write all the steps. I actually have the work off camera right now. I'm kind of glancing at it. I've worked through it previously. If you need to see the work with u substitution, feel free. I will say this, because of the x squared plus 4, we'll have a 2x. I don't want 2x. I need a 1x, so I have a 1/2. And in the process of getting that 1/2, I'll take the 1/2 and divide it by, when I add 1 to -3, I get -2. 1/2 divided by -2 is going to give me -1/4. So I'm just telling you where some of the numbers are coming from that you're about to see. And it's this, -1/4 x squared plus 4 to the -2. And all that takes place from 1 to b. Okay? And that's what I have right there. So now I'm going to use the fundamental theorem of calculus. We'll plug in the b here, we'll plug in the 1 here, we'll subtract them, we'll see what happens. So this might make me run out of room a little bit, but we'll go for it. So the limit as b approaches infinity of, I'm going to rewrite it as I do this too, by the way. So -1/4, and then we'll put that in the denominator. So b squared plus 4, b squared plus 4, and he is now squared, minus -1/4 of 1 squared plus 4, squared, left off a squared there, not that it matters, I'm squaring a 1. And we'll see what happens. Okay, so as I approach infinity, as b approaches infinity, then this gets bigger and bigger, my denominator is getting bigger, it's overpowering my numerator, so this term becomes 0 as we approach infinity, or approaches 0. And this term is 1 squared plus 4, squared 25 times 4 is 100, so 1 over 100. So I really have 1 over 100. Okay, let me warn you here. I have 1 over 100 for this improper integral. This does not necessarily converge to 1 over 100, but what I do know is that it converges. Because this integral converges to something, this converges to something. Not necessarily the same thing, rarely the same thing, coincidentally if it does happen. So I can't say this becomes 1 over 100 if I add them all together, no, but I do know it converges. So I'm going to say the series, and I chose that word carefully. I'm dealing with a series now. Because the integral converges, the series converges. The series converges. And just to continue to articulate what just happened, I'm going to continue that sentence. The series converges because the integral converged. Integral converged or converges. Well, the direct comparison test is one that we can use when we are going to, well, compare the series that we have to another one. So let me use an analogy that I've used before. If I was to look at someone that's 7 feet tall and say, they are tall, they are the standard for height. 7 feet, they are tall. And then someone taller than that walks in, are they tall? Well, of course they are. because they're taller than what I have defined as tall. Or if I say, man, so-and-so is short and they're a certain height, and then someone else shorter than them walks in, then they are considered short as well if my standard is a certain height and they fall below it. And it's the same idea here. When I have a direct comparison test, what I'm going to do is say, well, if this series converges, if I know some series and it converges, then another one that is consistently smaller than that also converges. Or if I know of one that diverges and then there's another one that's consistently larger, then it diverges as well. It's that idea. So let's take that, run with it, and write a few things down. When do I use it? Well, I use it when a given series has similarities to a series of known convergence or divergence, and I'm going to abbreviate because I'm running out of room. But if I know another series that has convergence or divergence, usually p-series, those are the ones that are really easy to identify. And if I can compare it to a p-series or a geometric, those are pretty easy as well, then I can pretty much say if it converges or diverges based on whether it's greater than or less than that. One other little caveat I need to throw in there, the terms must be positive. Terms of the series must be positive. Okay, so what does it tell me? Well, same thing I'd said with the analogy about height and shortness. So if each term, every term of a series of a given series, the one they gave you, series, well, I can spell it, series, there we go. We'll stop right there. If each term of a given series is greater than a divergent series, let me word this a little bit better. Then each term of a divergent series then the one they gave you, the given series, diverges. Then, this is wordy, the given series, the one you're trying to determine, it diverges. If each term of a given series is less than each term of a convergent series, you know where this is going, then the given series converges because it's smaller than something that approaches a specific value. Converges. Okay, so I've left no room to do the problem. Oh well. I think we won't need too much space for it. Here's number 9, and we want to do an example where we go from 1 to infinity. Let's see, what did I put? 1 over 6 to the n, and then plus 2 also in the denominator. Okay, well, what does that look a lot like? Well, that looks like 1 over 6 to the n, right? Okay, so I'm going to compare it to, directly compare it to 1 over 6 to the n. So we're going to compare to the sum from 1 to infinity of 1 over 6 to the n. That's what we're going to compare it to. Now, let's figure out what happens with this guy right here. So I look at that and I say, well, as 1 over 6 to the n, we could go a little bit further and we could say that this is really, I'm running out of space, n equals 1 to infinity. This is like 1/6 to the n. That's geometric. It's a geometric series. The common ratio, r, is between -1 and 1, so this converges. So this converges. I know my handwriting is just all kinds of ways here. So we're going to compare it to that, which converges. So now what I want to do is say, well, maybe this is actually less than that, so it converges too, right? So every term of this should be less than that. And so we're going to see if that's actually true. So I'm going to just kind of write it down, and if it's false, then I'll make some changes. So 1 over 6 to the n plus 2, it had better be consistently less than 1 over 6 to the n. And I'm wondering if this is true. So This denominator is bigger and always bigger. Because the denominator is bigger, this fraction is smaller, so this is true. So the given series, because this is true, the given series, the one they gave me, also converges. Converges. There we go. There are times that this is inconclusive. Like if I wrote this down and this wasn't true, then I would have to say, well, that's not necessarily true. So if it's greater than something that converges, what can you say? Well, you can't. You'd have to try a different tactic. Or if it's less than something that diverges, similar idea. The comparison test is a lot like the direct comparison test, which is why I left this statement up here. So you can go ahead and copy that if you like, or draw an arrow saying it's the same thing, but I do want to kind of walk you through it. Again, so when I have some given series and it has similarities to a series of known convergence or known divergence, usually a p series, those are the obvious ones, then I can use a limit comparison test rather than a direct comparison test. This one really comes in handy. The terms of the series must be positive, just like the last one. So here goes. What does it tell me? Well, let's talk about how we use it. For a series, let's call it the given series. That's the one they're giving you and they're asking, is this convergent or divergent? For a given series with terms that are an, for example, and a known series with terms bn, I know it as in like it's convergent, divergent. If, now here's where the limit comes in. We're going to divide the limits. So the limit as n approaches infinity of an over bn is two things, finite and positive. Then what? Well, I know one of them, so this will tell me what happens to the other one. Then both an and bn have the same, looks like sane, maybe it was going crazy, same convergence or divergence, and I will abbreviate that. So they have the same convergence and divergence. So I pick the one that I know, I compare it this way with the other one, and then whatever I get will tell me, well, if it's finite and positive, then I'll say, oh, well, they have the same. So then I'm able to talk about the one they gave me. So then that leads us to example number 10, which I will write in this corner here, and it will be this. And equals 1 to infinity, 1 over n to the fourth minus 3. Now your first thought might be, let's do a comparison, direct comparison test, and that kind of falls apart with this one a little bit because of that subtract 3. So the denominator isn't always consistently larger, and so this one, the limit comparison test, comes in handy when the direct comparison test falls apart. I like to look at it that way. So we're going to compare this to this one right here. So n equals 1 to infinity. Well, let's find something that looks kind of like it that's a little bit obvious, and that would be 1 over n to the fourth. There we go, 1 over n to the fourth. Well, what is 1 over n to the fourth? Well, it's a series. What kind of series? P series. I didn't give you any wait time on that question at all. P series, now you know. So it's a P series. And what does it do? Well, P is 4, so this one converges. So let's compare that to that, which converges. So what we're going to do is divide this one by this one. Now, you could do that one over that one, and that would be inconsistent with what I wrote, but you're going to get the same ending answer. You'll get a different limit, possibly, but you'll get the same ending answer. So here goes. The limit as n approaches infinity of 1 over n to the fourth minus 3 over 1 over n to the fourth, and this is where your knowledge of horizontal asymptotes comes in very handy. The limit as n approaches infinity, and this flips that up, so we have n to the 4 over n to the 4 minus 3, and as n gets bigger and bigger and bigger, they're basically the same thing at the top and the bottom. Subtracting 3 isn't going to be a huge deal when you're dealing with infinities, so that's equal to 1. Okay, 1 is clearly finite, it is clearly positive, therefore both a and b have the same convergence or divergence? Well, the one I picked converges, so the one they gave me also converges. So I'm just going to write that in a statement. I'm going to just write down the one they gave me, and the 4 and then minus 3 converges. There we go. It converges because the other one converges. And that is the limit comparison test. Well, let's talk about the alternating series test. When do I use it? I use it when I have a series that's alternating in its sign. And those are of this type of structure right here. They go from 1 to infinity, and it's -1 to the n with some other recursive formula, a sub n, not recursive, explicit formula. And it could look like that, or it could look like this right here. Couldn't think of the word. It's explicit. The word is explicit. I can tell you what it is. The word actually is explicit. But there's your explicit formula. But this is the factor that toggles things back and forth, toggles the sign back and forth. And that could be n-1. There's lots of different ways it can look. But basically you have some sort of factor that is changing your sign back and forth from positive to negative, positive to negative. So depending on whether this is odd or even, it flips it back and forth. Well, what does it tell me? It tells me that my alternating series converges when I meet two conditions. And here's condition number 1. The limit as n approaches infinity of the non-toggling part, like the absolute value part of my series, when the limit as n approaches infinity of that equals 0. So basically this is like the nth term test. So you could look at this and be like, oh, well, you know, that's the nth term. Because if this was anything other than 0, like if it just kind of kept on going and you got bigger and bigger and bigger, then it would diverge. But anyway, it converges when that is true, and also when any term, now again, the positive portion of a term, is less than or equal to the one before it. So I have some term and then I have the next term. So the next term had better be less than or equal to the one that was before it. So it's getting smaller or at least staying the same, okay? So let's do an example, and this shall be example number 11. There we go. And it's going to look like this. I like this one. N equals 1 goes to infinity. It is going to be -1 to the n, 2 to the n over n factorial. Okay, well, I need to satisfy two conditions. First condition, I need to make sure that the limit as the non-toggling part, the non-negative part, does approach 0. So let's go ahead and figure that out. So I need to see if the limit as n approaches infinity of not the negative stuff, 2 to the n over n factorial, if it equals 0. And if it does, then I've satisfied one of the two conditions. And so let's see, what's more powerful, exponential or factorial? Factorial, definitely. That grows bigger faster. So your denominator overtakes your numerator. So this truly does approach 0. We've met condition number 1. Put a check if you want to, or just smile, either way. So condition number 2, I want to see if this component, again, I'm ignoring the negative aspect of it. I want to see if this, when I go to the next term, n plus 1 factorial, is less than or equal to 2 to the n over n factorial. If this is a true statement and I can put a check here, then yes, it converges. Otherwise, no, it doesn't. So let's keep tinkering with this and see what it looks like. I'm going to change this a little bit, and it might be common sense to you that this is true, and it is true, so this does converge. So 2 to the n times 2 over n factorial times n plus 1. So like n plus 1 factorial is n plus 1 times n times that, and it goes all the way back to 1. Less than or equal to 2 to the n over n factorial. And what you could do is divide out 2 to the n, and we'll do that. I'm going to divide out 2 to the n, so those cancel. I'm going to divide out n factorial, and what I'm really left with is the wrong side of the marker. Here we go. What I'm really left with is, that brings it over here, 2 to the n, sorry, just 2 over n plus 1, and that is less than or equal to 1, because we divided both of those out. Okay, is this a true statement? So 2 over n plus 1 is less than or equal to 1. Well, what n values am I dealing with? Well, n goes from 1 to infinity. So if I plug in a 1, I have 2 over 2, less than or equal to 1, true. If I plug in a 2, I have 2 over 3, less than 1. And then 2 over 4 and 2 over 5 and 2 over 6. And so it's consistently less than 1. So yes, this series converges. I'd write it over here, but I'm out of space. This series converges. And there we go. If we know this is true and this is true, then we can say that it converges. So what's the best time to use the root test? Well, whenever you feel like it. So actually any series works, but some are more practical than others. So any series that you want to use this for, use it any time. But here's the kicker for me, especially exponentials. Okay, exponentials meaning it's going to be raised to the nth power or whatever. So what does it tell me? Well, it tells me 3 different things. Well, 2 different things and then one that's inconclusive. So if I take the limit as n approaches infinity of the nth root of the absolute value, because we've got to keep it positive, right? Of a sub n, and I get 3 different things, and I get 3 different answers. So if this, I'm putting a colon just to kind of finish my thought. If it's less than 1, then the series converges. And I'm going to go a little further. I'm going to say it converges absolutely, meaning that if it's an alternating series, then its positive converges and its alternating back and forth would converge. So converges absolutely. Converges absolutely. If it is greater than 1, or you could say equals infinity, which of course is greater than 1, but yeah, slightly different category, then the series diverges. And if it equals 1, then the test is inconclusive. Okay, interesting. So we have a little bit of space. Let's do one of these, and these are actually pretty straightforward if you use it on the right ones. So here's number 12. N equals 1 goes to infinity, and we're going to do this one. 3n plus 7 over 5n minus 1, and that is to the n power. Okay, notice that I'm going to use a root test on this one because it's to the n power. So I'm going to take the nth root of something to the nth power. Well, those are going to cancel out. Lucky me. And then I'm left with just something that's very simple to deal with. So let's do it. I'm going to take the limit as n approaches infinity of the nth root of the absolute value of 3n plus 7 over 5n minus 1, and that's all to the nth power. And when I do that, the nth root and the n power cancel each other out, and I'm left with the limit as n approaches infinity of 3n plus 7 over 5n minus 1. The absolute value is there, so you're not taking the square root or something of a negative kind of thing. But basically, if I do this, then, well, I'm going to use my common sense horizontal asymptote understanding here. So 3 over 5, right? 3 over 5, and 3 over 5 is less than 1, so the series converges. And I'm going to leave it at that. You could say absolutely, but I don't believe this thing alternates back and forth. So there you go. The series converges. That is all you have to do with those. I think the biggest giveaway about when to use it is if you see an N or a K. They often use K. If you see one of those up there. One more test for convergence, and it's the ratio test, and we're going to be, well, using a ratio. So when do I use it? I can use it almost any time. So anytime you want to. So there's no specific type of series that you may want to use this on. It's pretty practical and it's very useful. And from an algebraic standpoint, it's kind of fun too. Anyway, so anytime on any series. Now there might be some that are more practical than others, but that's when you can use it. So what does it tell me? Well, it's a lot like the last test, the root test, in that we have 3 different categories for what it could do. But first, let's write down what you have to do. So if the limit as n approaches infinity of, now we're going to do an absolute value here because if it's alternating, we just want to pretend like it's positive. So a sub n plus 1, that means the next term. divided by a sub n, and that's the current term. If that is, and I'm putting a colon here, and from there I'm going to branch off into three different statements. So if this is less than 1, then the series converges. And not only does it converges absolutely, meaning if it was alternating, then that converges, and if it's positive, then that converges. So absolutely. If it is greater than 1, then the series diverges, and it's a lot like the last test, like I said. So this idea is the same. If it's equal to 1, then the ratio test is inconclusive. Okay, so let's do an example of that. And the only difference really between the last test and this test is the way this part is structured right here. So here goes. Let's do number 13. N equals, well, what do you want to start at? You want to start at 1? Let's not. Sometimes they start in strange places like 0. And that's perfectly okay. This is going to be negative 1 to the n, 2 to the n over n factorial. So there we go. And I want to know if this converges or diverges. So if I wrote all these terms out, would it converge or diverge? This is an alternating sequence, by the way, a series, by the way. That negative 1 to the n is going to switch the signs back and forth from one sign to the other as you proceed forward. However, when I deal with this, I'm going to do the absolute value, meaning I'm going to drop that negative 1 to the n, right? So here goes. I need the limit. This is where the algebra gets fun. It's going to be great. As n approaches infinity of this, but I need the next term. But when I say this, I really don't need all of this. I need the absolute value of it. So again, I'm ignoring the negative stuff. So 2 to the n is positive, n factorial is positive, and so we're just going to deal with that. So 2 to the n plus 1 over n plus 1 factorial over, and I'm not putting the bars because I'm really taking care of that when I took out that factor of negative 1 to the n, over the current term, which is 2 to the n, over n factorial. And let's keep going with it and hope that we don't have to run into that and erase some of it. So the limit as n approaches infinity of, okay, so 2 to the n plus 1 is the same as 2 to the n times 2 to the 1, right? And that is over n plus 1 factorial, which is really n factorial, and then you went one more, so times n plus 1. And then this would be reciprocated and brought up, multiplied, so times n factorial here, and then 2 to the n here. And then we have some obvious cancellation that can take place. So we have n factorial that's gone. We have, wow, you really can't even tell it's a different color, can you? 2 to the n, it's orange. You have to get right up on it to see that. And we are left with the limit as n approaches infinity of 2 over n plus 1. Well, as n gets big, the denominator gets huge, and it overpowers that numerator, so this is 0. Okay, we look at it and we say, well, I've done that, and I got something less than 1, so the series converges absolutely. So I'm just going to write that down. The series converges. Does it converge? Absolutely. Great joke. It converges absolutely. So the toggling back and forth converges, and if it was truly positive, then it would converge as well.